2017 Innovation Audition Awards. 2 years ago, the winner was Impossible Objects. Last year, the winner was InScript. And so this year, we have 9 5-minute presentations. They're going to start just in a few minutes. So if you download the app, you can vote on the app starting at 1:30 at the end of all the presentations. So just let me quickly introduce our judges. We have Brian Levy from Joe Gibbs Racing, Boris Fritz, who's former Northrop Grumman, Brenna Snyderman from Deloitte, and Carl Decker from Metalflow. Stand up, judges. Come on, let everybody know who you are. And then the first presentation is on Metal X. It's from John Riley at Mark Forged. John?
Good afternoon, everybody. I'm John Riley. I'm from Mark Forged, and today I'm going to tell you about atomic diffusion additive manufacturing and the Metal X printer. But first, I want you to take a look at this. This is interesting. This is a copper awl, and it was recovered from a grave in Israel, a historic dig, and they carbon dated that dig to between 5,000 and 7,000 BC. And it was formed, the interesting part about this metal artifact is that it was formed through molding, which means humans have been pouring metal into molds for over 7,000 years now. But now we have 3D metal printing. But today we're still kind of living in the time of mainframes. 3D metal printers are large, they're complicated, they're difficult to operate, you need a dedicated operator. They're the mainframes of printer machines, and as history shows, mainframes get displaced by blade servers. And what that means for 3D printers is a world of low-cost, high-precision machines working in racks, providing on-demand production. And so what I'm going to talk to you today about is how you cross the bridge from the mainframe of 3D printing metal to the server farm of 3D printing metal. Like many great innovations, how this is accomplished lives at the intersection of 2 existing technologies. I don't think it was immediately obvious to anyone when you combine the internet with a phone, the types of changes to our work and life it would unleash over, it's been almost 10 years since the iPhone was launched. Now you have apps, maps, payment mechanisms, an application for the show, download it and vote for your favorite competitor here. It's really changed everything, and in the very same way that 2 seemingly well-known technologies combine to unleash innovation, that's what atomic diffusion additive manufacturing has done. It lives at the intersection of extrusion, which is a well-known technology, and metal injection molding. So at Mark Forged, we've been using reinforced extrusion for a long time. We take chopped carbon fiber, we add it to a nylon matrix, and we print it. In metal injection molding, what you do is you take metal powder and you bind it in plastic and you inject it into an injection mold. And so what we do here is basically take that metal injection molding material and just print it into your part. The great part about that is that now you can additively create the part, and you're leveraging 2 known technologies together. We launched atomic diffusion additive manufacturing, we call it ATOM, in January at CES. And we believe over the next 5 years, this is really going to change the way we work and change the way that parts are made. Okay, so let's talk about how it actually works. You start with that plastic that has the metal powder bound in it. Now it's non-toxic. You can handle it. It's easy to use, and you print it just like normal. Although during the sintering process, which we'll get to, your parts shrink a little bit. So you actually have to print the part a little bit larger than your expected final outcome. We're going to automatically scale them for you in software. And when you're done, it's not stuck to the build plate or anything. It's just like a normal part that you would get off an extrusion printer. You're able to use any of the metal injection molding materials, which means suddenly you have access to hundreds and hundreds of different metal alloys that can all be used to additively create parts in exactly the same way, just like you would extrude plastic on any one of the printers you'll see around the show floor. Once the parts are printed, you have what's called a green part. And this is very, very similar to the part that comes out of a metal injection mold once it's been molded. Here what we've done is these are a row of Ducati brake levers that we printed. And what we've done is we've paused the print before we finished on some of them so that you can see that there's something interesting about the ability to create a part this way, which is we're able to create captive infills. You're looking at a 50% triangular infill on the parts that we stopped. So now not only do you have that sort of great design flexibility that you already get with additive manufacturing, but you can also create lighter weight parts with captive internal geometries with no powder inside of them. And this is going to give you a lot of the strength that you know from the metals that you know, but it actually uses less material. So at the end, you end up with a part that's actually surprisingly affordable because you don't have to build the entire solid part to get your part. You can construct it with the infill. Okay, from here onwards, it's effectively metal injection molding. So you take that green part, you wash it in a solution to remove a lot of the plastic binder, and then you stick it into a sintering furnace. You heat it up to 85% of the melting temperature of the material, and the metal powder diffuses into itself, shrinks about 20%, and you're left with a solid metal part in the material that you chose at about 99.7% density. So you're able to get like fully dense metal parts out of it. We'll just take a look at what those look like. Here you go. So now you can manufacture these metal parts with greater flexibility of design, with lower total material contributed to the part itself. And then if you have to make a change, it's easy. You can just simply change your CAD file and print it, and you have your new final part the next day instead of waiting around for this entire molding process. So you get less material and no molds. So for the first time, we're really changing 7,000 years of history. So this is the Metal X. It's the first atom printer. We unveiled it at CES this year. And it's built on our 4th generation reinforced extrusion platform. So we've been doing this for quite a while. We know how to make great parts on it. It ships in September. But where is it all going? That's the key part of this innovation. It's not just smashing the internet and a phone together, but it's going to unlock some stuff downstream that's going to be really important to the industry. And it's called parallelization. With atomic diffusion additive manufacturing, we're going to unlock the ability to create metal print farms. So you can have racks of thousands of low-cost, like think $1,000 per print head instances, all running in parallel, all run by one software program that load balances it automatically. If you lose one of those printers, if it goes down for some reason, a part breaks on it, instead of losing your entire production capacity, you've lost 1/1000th of your production capacity. And the software will automatically rebalance the load. If you need to use 2 or 3 or 10 different materials, you can spread your production capacity across the print farm. It's easy to use, and the parts are cheap because they use minimum materials to get to the strength that you need. So we're going to get there on cost. We're going to get there on capacity, and that flexibility means now you can go from your design almost directly into production on the server farm. So this is how you replace the mainframes that we have today in metal 3D printing. This photo, by the way, is a photo of Google's server farm. They don't run on a mainframe. They run on over 1 million instances of blade servers, and that's how they're able to scale, and that's the same way that you're going to scale in metal additive manufacturing in the future, all unlocked by combining 2 technologies that exist today in a new and interesting way. Okay, thank you.
Thanks, John. Next up on rapid part distortion supports and builds failure prediction using simulation is Chris Robinson from 3D Sim.
All right, so as he mentioned, I'm Chris Robinson. I'm the Director of Application Engineering at 3D Sim, and we're going to talk about what we can do with simulation to predict part distortion, supports, and build failures. And we'll see if I can use this thing correctly. So to start off with, for those of you that have built parts before in Metal AM, you've probably seen things similar to what we see in these pictures on your far right, I guess my left. The top part is a part that was building, and the part itself failed, split apart and cracked. The next one is support, delaminating from the part. And the bottom one is something that just kind of ruins your day when you come in the morning and you see that you've got a part that crashed, and that bottom right-hand picture is a picture of the blade that has crashed into a part. So in Metal AM, we often run into different types of build failures. So 3D Sim is trying to address that particular problem. In just 2016 alone, there were millions of dollars wasted on failed AM builds and non-conforming parts. So nearly every AM user's schedule has been driven to the right because of trial and error experimentation. And predicting the outcome of the Metal AM powder bed process is extremely complex. But Exosim, until the release of Exosim, then the prediction tools and the finite methods that were available had not been able to provide the user with distortion, stress, blade crash predictions, support and part failure predictions in a reasonable amount of time with appropriate accuracy. But, and so that has led to additional trial and error still being used to develop the appropriate machine parameters, equipment, designs, support structures, and part orientations. So as we deal with that particular problem, which is a very widespread problem, not just across metal AM, but across the entire AM industry, 3D Sim's Exosim software is a solution to that problem. Is what we provide is distortion prediction. So if you see over there, you've got those two filters. One of them has got a bulge in it. The thing next to it is our prediction of that bulge. So not only do you get just material shrinkage predictions, but also that particular bulge is based off of the compressive loading and that ring on top of it. So you're getting mechanical loading distortions as well. We can compensate for the distortion in the part, so we can compensate your geometry so you'll get what you want. Residual stress predictions, automatic support generation, so you no longer have to waste time trying to generate your own supports and trying to determine what will work. Potential blade crash detections. You can look at the picture on the bottom left of this propeller blade. We identify where your part is likely to interfere with a recoder blade. And then support failure prediction as well. Exosim gives users a unique opportunity to be able to use both thermal and mechanics solvers coupled together to predict the most important aspects of an AM build, which they cannot get anywhere else. So we have an assumed uniform strain mode, which is kind of our version of inherent strain. But then we also have the scan pattern strain, which is unique to 3D Sim. And it's based off of the scan pattern of your part. Very, very rapid simulation, but utilizing some of those process dependencies. And then we have thermal strain, which is completely unique to 3D Sim, where the simulation is based off of in-depth material and process details. And so users of Exosim are already turning these trial and error experimentations into 90% first-time success rates by trading that trial and error, the iterations, for Exosim. And I think it's pretty easy to see the benefits and the value, but it's spread across the entire industry and across the entire supply chain. A few examples are that designers can save time and money in being able to predict and understand and correct distortion and residual stress. Machine operators, they can save time and money in selecting the orientation of their part and being able to generate those supports, avoiding blade crashes, avoiding support failures, and avoiding the recalibration and maintenance issues that come from crashing your machines, or just the added maintenance that comes from having to run all of these extra builds on your machine. Suppliers are able to provide higher quality parts on time. Project budgets and schedules, instead of doing the normal moving up and to the right, you can start to drive them down and to the left by using predictive simulation. Everyone sees greater ROI in AM by avoiding waste, which leads to greater adoption of AM in general. And then there was a project that GE was leading through America Makes. We were a part of it, where in that report, we report a 75% reduction in part development time by being able to use prediction and distortion compensation. And one of the key benefits of Exosim is that a single build crash or a troublesome part can cost more than an entire year's subscription of Exosim. And that's all I've got. If you want to see how much you can save, come and visit us at 3dsim.com. Thank you.
Thanks, Chris. Next up is Additive World Platform, Ilko Bozeman from Additive Industries. Ilko?
Thank you. Good afternoon. I think what we can learn from today and what you can see is that software has an increasing role in additive manufacturing. And that's not very difficult because equipment has been around very long. It's been used mainly in prototyping purposes. But what you see when it comes to additive manufacturing, so industrial applications and industrial adoption of the technology, you see that there is a lot more benefit to be gained when you combine hard and software. That's what we do with our Additive World platform. What we do is we looked at what is the additive manufacturing promise? What does additive manufacturing promises to deliver for industrial applications? And where we are at the moment, how far are we from what industries want in their industrial applications? And we identified that there were a number of issues. And those issues are on the application side, the design side, the software side, and also on the equipment side. We tried to solve them on one hand by developing industry-focused, industrial-focused applications and systems, equipment, but you cannot do that without the software combined to it. So what we do in the Additive World platform is provide a full suite of software that supports the user in the entire workflow of additive manufacturing. Not only the data preparation, but also the manufacturing, equipment monitoring, but especially the data logging, because the data logging is key in additive manufacturing. What we see, what you want in industrial applications is you want to increase productivity, you want to ensure uptime of your systems, and you want to increase your product and process quality. The only way of doing that is collecting your data, analyzing it in a structured way, and learn from what you do now and do it better tomorrow. And that's why we launched the platform. In order to do that, we don't want to reinvent the wheel. We're basically a manufacturer of equipment, but we also think that software is important. But there are very valid tools in the industry. There are CAD tools available. There are simulation tools like 3D Sim available. So what we do is connecting all those systems into our platform and making sure that you can allow to use the data that is generated by those tools in your entire manufacturing process. So that leaves me with thanking you for your attention, and join us in focusing what matters most in industrial application, and that's increasing productivity and not being worried about what data is where, solve it in a proper way, and increase your productivity. Thank you very much.
Thank you, Wilco. Next up is Topology Optimization from Steve Pills from ANSYS.
Thank you, Dan. ANSYS is an engineering simulation company. It was 50 people in size when I joined in 1987. It's now the world's largest engineering simulation company. And our customers are coming to us trying to get their hands around engineering simulation for additive manufacturing. So we've got 45,000 customers coming to us saying, hey, can you help us figure out additive manufacturing? What does this mean for me? What's the opportunity? How do I deal with this? How do I validate my parts? How do I design for this? So I'm talking today about one very small aspect of what we're doing, but lattice structures is very important, a very emerging field because there's lighter weight, there's things we can do that we cannot do otherwise. So I'm going to talk today about topology optimization of lattice structures, which is something that's a little bit unusual. So many companies will allow you to take a lattice structure, put it into your part, but there's no engineering behind it. There's no physics. There's nothing driving this. So from an engineering standpoint, it's not an intelligent way to design. But this is what our customers come to us and say, additive manufacturing now frees me up to do design, very free design, but I need some guidance. Just because I design this way doesn't mean it's the right way. So we've been working with the University of Pittsburgh and America Makes on an additive manufacturing process for topology optimization. And we've been working on that for the last year or two. Customers are starting to use that. So the beauty of the America Makes project is that we were able to go from concept, publication, to software in our customers' hands in under a year, which is kind of unheard of in the software industry, but something the additive manufacturing industry, I think, needs. One of the previous speakers said, this is the year of software and additive manufacturing, and I think that's true, because customers need some guidance. How do we get pushed in? How do we kind of understand what we're doing? Yes, we can make these parts, but do they work? Are they going to shear off of my engine while I'm flying over the Atlantic Ocean and cause a real problem? So being able to produce is one thing, being able to produce it intelligently is another. Something that it's a very small part of it, but it's innovative in that it's a new area of study, is lattice structures called minimal surfaces. So it's a gyroid surfaces. There's many other surfaces that have applications here. You can kind of see it growing here. It's a lattice structure that has essentially no beginning and no end. So mathematically, it's very pure. It was something that was discovered way back in the 1700s, popularized by NASA in the 70s. But there was no way to produce these things before, because you cannot mold these things, you cannot cast these things, you cannot extrude them, form them. But with additive manufacturing, hey, complexity is free. Not quite free, but almost free. So now it's got the ability to produce these things that have lightweight, excellent fatigue resistance, great thermal characteristics, etc. So here's some examples of the parts that we put into ANSYS Space Claim, which is a booth across the hall, by the way, if you want to visit a little bit later. So this is a gyroid surface lattice infill that is non-topology optimized, and I'll show that to the judges here. So it's non-topology optimized. So just being able to make a lattice structure into a part, that's one thing, but being able to topology optimize it, that's quite another. So I'll hand this to the judge. Okay, so that's essentially a lattice infill, which I think many companies can do. A CAD company can do that. That's great. It works maybe, but what is the engineering behind that? So the beautiful part is then to do topology optimization on that lattice infill. Oops, go back one. Lattice infill. So now if we look at the larger version of this, we can see that the structure is strong where it needs to be and light where it doesn't need to be. So gyroid surfaces, minimal structures, infinite fatigue strength, great thermal characteristics, structurally strong where it needs to be, light where it doesn't need to be. Thank you very much.
Thanks, Steve. The next presentation is MI Workflow, Najib Beg from Granta Design. Najib?
Okay, thank you very much. So my name is Najib Beg with Granta Design, product manager for materials innovation. Before I go to the problem slide, I would like to ask you a question that will help you to understand the problem that this innovation is helping in solving. So is it important for you to be in control of your personal finances? Is it important to keep track on your expenditures, on your income, really so you know what money you're spending on? And related to additive manufacturing, is it important to you to have a business process, a consistent process for your information flow for additive manufacturing? All the data that's being produced from your test data to your build parameters, to your powder materials, so the whole complete additive chain. So if I move on to the next slide here. So there is today no consistent process for the additive manufacturing workflow. And when I say workflow, that's the process of keeping track of your build. So going from the request to the approval to the full qualification of your part. And also related to that is the data that's being generated throughout the process. And you can see all the different points there. Then that's just an example of the data that's being generated. And that's very important to capture in a similar way that you're capturing the information of your finances. This is equally important that you are in control of the whole workflow and the information that is being generated. So the solution is to have a system that allows you to capture the full workflow and the business process for additive manufacturing. I know it's quite a recent new thing with additive. People are doing prototyping, but when you really go into serious qualification, you need to have a consistent business process in a similar way that you have for your design process, for your HR, for your procurement, any other business process. There's no different for additive manufacturing. This is one example workflow that could be set up using the system. So on the left-hand side, you have the engineering department. They are requesting the builds, investigating the possibility of using additive. On the right-hand side, you could have an additive manufacturing lab that is doing the qualification and investigating the part information. So you can have the full workflow there designed for your organizational need to accommodate any process. Just a screenshot from the software. It's called MI Workflow. It's a web-based interface, a lot of app feeling to it. We know end users want a simple system, as easy as possible to use. So it's very drag and drop your CAD files, drawings, STL files. You, for example, assign your materials, estimated cost, finished time for the build. Really, it's a very flexible system in terms of allowing you to accommodate any process information that you need to capture. Just more on the details of what information could be captured. So here you can see the materials, the project information, cost estimation, who made the order, when it's going to be delivered. Going into more of the details, so these are the specific build parameters that we're capturing. all the parts, all the builds that was manufactured, the part information, the micrographs, basically anything that you can think about in terms of from qualification and onwards. Here we are capturing more complex test data that is vital to capture. Now this is very expensive testing that companies do. We work with companies like GM, Rolls-Royce, Boeing, because it's very imperative, important data that needs to be captured. In terms of analysis, so once you have the workflow in place, once you have the data, you are then able to leverage that information with data mining. So you can ask questions like, what is the optimal process parameter? For example, the speed of my machine, how does that impact my mechanical properties? So this is the flip coin of it. Once you have the data, you then need to understand it to progress your research and development. And really, it's I think I'll leave it up to you guys to understand the benefits of having a more efficient business process in place. And really, it could be time savings, cost savings. Engineers can focus on the more relevant things for research and development. So it's just quite a big, broad topic in terms of having a more efficient business process. But essentially, I would say it gets down to having a more competitive product, getting to market quicker, and being more efficient. Thank you very much.
Thank you, Najib. Next up is the Einscan Pro Plus multifunctional handheld 3D scanner. The presenter is Sheldon Shi from the Hangzhou Shining 3D Tech.
Hello, everybody. I'm Sheldon from Shining 3D. And today I will introduce you this new innovation. It's called Einscan Pro Plus. Okay, in current several years, there are more and more companies like emerge that they are inventing new 3D scanners, and also thanks to 3D printing industry, more and more 3D data are needed. Therefore, 3D scanners are so important. So, what are the major problems in the 3D scanner industry? Let's see. Okay, the first one is the price. I think this is always the biggest concern for all the consumers. So the problem is how to make a very powerful 3D scanners at a very affordable price. Then it will attract more and more consumers and generate more and more 3D data. And the second problem is that the data usage. As more and more 3D scanners emerge, we have a lot of 3D data. However, some data, they are not used effectively. For example, an engineer, he scanned a very simple product, then he got the 3D data, which is so not complex that he cannot use it as the reverse engineering. In other circumstances, some like college students or some high school students, they will use the 3D scanner to scan some projects. However, the process and the final output data is so complex that they cannot use it. So how to make all of them, how to make all the consumers to use all the data effectively is another problem. The third one, I think is the most important one, is that how to scan the details with very high speed. Because it sounds almost impossible that you can scan a very detailed product or a very large product at a very high speed. So I think we Shining 3D invent this Einscan Pro Plus can solve these problems. Okay, let's see how can we do this. The most important feature of the Einscan Pro Plus is that it's equipped with the handheld HD mode. What it does is that it will project 100 data capturing lines instead of 7, which the previous version has. So you can see it's almost 14 times the previous version. So it will greatly increase the scanning speed. Therefore, it results in the total scanning speed will increase greatly, and it will result in the scanning speed is like 550,000 points per second. It is like incredible. And besides that, the entire scanning range is 1.6 times enlarged than the previous version. So all these features combined together will greatly increase the scanning speed. Currently, we have a client called Speed Lab Racing, and they are using the N-Scan Pro Plus to scan a car. Actually, most people think that these kind of consumer or like consumer-like handheld scanners cannot even scan the whole car, but actually they did. And they also used this one to scan many other large projects, and they think this one is just like scanning so fast. Okay, besides the previous solution, we also have several other benefits and value. The first one is the one I mentioned before. The biggest concern of most consumers is the price. Like this scanner, the entire bundle of it include the industrial parts, include the color module, and all the tripod and scan table. All of them include together are only cost less than $6,000. So compared to all the other high-end industrial 3D scanners, it is relatively cheap. And the second value is that it uses the structural light and the laser scanning technology. It makes it can scan the entire model at a very high speed and also have very high accuracy. So you can see here the accuracy can go down to 0.05 millimeters, and it is also very competitive in the market. The third benefit and value is that the N-Scan Pro Plus is a modular system. As I mentioned before, the entire bundle costs like $6,000, and it includes the industrial module and color module. But if you only need some part of it, then you just need to purchase the modules you want, and you don't need to pay for the other parts. The final benefit is that it can export both the watertight and unwatertight STL files. And this is very important because this affects the data usage effectiveness. As I mentioned before, if an engineer he wants to do some reverse engineering, then he just need to scan a model and export it as a unwatertight ones, and then he can just use this data to do some reverse engineering. But if a student, like high school students, want to 3D print some parts, then he just need to use the scanner to scan the parts and export it directly to a watertight STL files, and then he can just import this file to a 3D printer and print as the final model. These are the four benefits of the N-Scan Pro Plus. That's it. Thank you.
Thanks, Sheldon. The next presentation is on secure digital supply chain software. Stephen Thomas from Identify 3D. Stephen?
Good afternoon. I'm Stephen Thomas. I'm a co-founder of Identify 3D. We're a software company, startup out of San Francisco. So yes, we started in a garage first. We had to tick that box. We are a software solution. We heard a lot about data through 3D Sim or Granta, the importance of data in digital manufacturing. We protect that data. That's our focus. We provide secure protection of data end-to-end from the time of the design all the way to the manufacturing process, and doing so enabling quality and traceability. And why does that matter? The supply chain or the manufacturing is changing. We're all here to kind of learn about it, or we're just stakeholder in it. And the traditional supply chain, you forecast, you manufacture, you distribute, and you're going to have a product on the shelves, and then someone will buy it. The promise of digital manufacturing is that the distribution will happen in a digital form. So now you have files that have either designs, informations, a lot of engineering information, simulation informations, and those files will move in the supply chain in a digital form before a product gets built. And I'm sure you can come up with a couple of examples of other industry and what they went through once their high-value IP assets went digital. Lots of new risk. So we all know all the benefits of potentially this digital manufacturing vision, which is to enable decentralized manufacturing where you can manufacture things on demand at the time of need. But with that comes a lot of new issues and challenges at the design phase, at the distribution phase, at the manufacturing phase, and the in-field phase when the product is now in a physical form and moved through the supply chain. So our solution has been to not replace anything of that flow, but build on the top of that flow. We have different components that goes into each of the phase. One of our components is called Protect. This is the part of the software that will do the encryptions of the file, the protection of the file. It'll create a secure container where you can put any sorts of information, whether it's an STL file, a G-code, or any type of engineering data associated with it. That protected container now will move through the supply chain, and then we have an element called Manage, which would distribute license associated with the container. Those license, there's two types of license. There will be the business license, which reflect the contractual relationship you have with your stakeholder. So who has the right to manufacture how much for how long? And then the manufacturing informations. What type of machine can manufacture that? What type of material should be used? And how the machine should be set up. And those parameters will be enforced at the level of the machine. We're developing relationship with machine manufacturers. We are a very strong partner of Siemens, which is a big player in subtractive technology. Same issue. Our solution applies to additive and subtractive. And then we're building partnership to trace once the product is in a physical form. So the benefit, I'm sure I've talked enough about it, it's the control of your IP. So you prevent from illegal distribution, from copying, from modification. The manufacturing repeatability, now that you're licensing your IP, your data, you're also constraining how it needs to be produced. So it will enable manufacturing repeatability, whether you send a file in one place or another place, we'll look for the same outcome. It's all about the movement of data. I mean, there's been like 3 companies presenting about managing data, so all that logistics of moving data around. And then we'll enable compliance. Compliance, because everything is in the licensing engine, compliance, ITAR compliance, any type of FAA compliance, all sorts of compliance that are specific to the industry you're in. So we have a booth, 2352. There's a lot more to what I just said in terms of the technology. We work with very large Fortune 500 companies on those topics. We are, as I said earlier, a big partner of Siemens and others. So if this is a topic of interest, please come and talk to us. Thank you.
Thanks to Stefan for that presentation. The next presentation is novel titanium alloy for medical devices using additive manufacturing, Swee Long Sing, Singapore Center for 3D Printing.
Good afternoon, everyone. I'm Swee Leong from the Singapore Center for 3D Printing. We are not a company, we are a research institute located in Singapore. What I'm here today is to talk about the new material that we created specifically for medical device using a powder bed fusion process. Why titanium alloy? Because it's the most commonly used alloy in the medical field currently because of the biocompatibility, high corrosion resistance, and of course the lightweight and superior mechanical properties compared to other steel-based or cobalt chromium-based alloys for similar applications. However, titanium alloys have a fundamental problem, which is the mismatch of the stiffness or young modulus compared to our bone. So it limits the way that it can actually be used in implants or other medical devices applications. So what are the potential solutions that we can see? Some people usually look at new product design, like lattice structures, specific custom-made implant to reduce this modulus problem, or even new processes developed for AM or subtractive manufacturing, conventional methods to produce implants. But the fundamental problems that we should look at is actually materials development. AM itself, as a new manufacturing process, actually provide us with advantages and potential to create new materials that are impossible to create using previous alloying methods. So what we do is we use powder mixture made up of titanium and tantalum, which are also popular for biomedical applications. And why are these different from other powder bed fusion technology that use? Because powder bed fusion technology predominantly use pre-alloyed powders. That means within each powder particle itself, it is already pre-alloyed that consists of the composition that your material wants to be at the final part. Whereas for us, we use powder blends that provide us the opportunity for in situ formation of the alloy as well as the functional parts in one single step. This actually allows us to skip the pre-processing of alloying the material. And how does this benefit us is that we can actually provide homogeneous alloys that are impossible to create because of high melting temperature by conventional methods, and the performance are actually similar to using a pre-alloyed material. This allows us to skip the step while maintaining the mechanical properties. So we benchmark this titanium tantalum alloy that is produced with conventionally used titanium 64, which is very popular in the market nowadays, and pure titanium. And we actually see improve in mechanical properties and performance, such as a 42% reduction in modulus, which is a reduction of modulus stiffness and bring it closer to human bone, while maintaining a higher mechanical strength compared to pure titanium. Even in lattice form, we also observe similar trend in improvement in mechanical properties compared to pure titanium and TI64. And of course, since we are targeting biomedical devices, we have to do a simple biocompatibility test using osteoblast cell lines, and we observe similar comparable biocompatibility of these new alloys compared to the commercially available material, which give us potential to actually create this new material for specific medical devices. And there are already demand in the market for this material, and we are in talk with several hospitals and implant manufacturer to bring this innovation one step closer to the market. So if you are interested, I can be contacted through my email, my mobile number, and we are at booth 950 actually at the exhibition. Thank you.
Multi-material, FFF Biomimetic Solutions, Aaron Chow, University of Michigan, Neuroprosthetics. Aaron?
Thank you. So I'm Aaron. I'm from the University of Michigan, here to talk about our work actually with soft materials and replicating tissue durometers. So right now, we're in a place where in 2013, the group Enable showed us the world that you could actually 3D print prosthetic devices for anybody who needs them for a relatively reasonable cost. Now, the problem with a 3D printed prosthetic device is similar to that of a normally manufactured one. One of the huge problems is the exoskeletal nature. So if you take a look at your hand, you have a skeleton inside that's nice and hard and stiff that's providing structure, but then you have tissue depth all the way around every single surface. This allows you to grip things, it allows you to grasp things, and it also gives that human non-mechanical property when you're interacting with other humans. So the current solution to the industry with prosthetics is actually to have an artist custom make a full silicone sleeve. So this will be a $10,000 to $20,000 project. It'll take an artist a few weeks and it'll look fantastic. Now the problem is when you put that on, you're inhibiting actually mechanical movement of the device and limiting the interactions that it can do. And the problem with this is it's relatively inaccessible due to the high cost and the low availability to people. And another thing to think about with the hands is what you bring along with tissue is also your fingerprints, which is a really important identifier for a lot of people, whether it's the government, a school agency, or even your phone. You interact with technology with your fingerprints, and when you lose a limb, that's another piece of your identity that you lose. So mainly I work with the pediatric market. We're not focusing on how to replace currently built prosthetic devices, but we are focusing on ways to make prosthetic devices affordable to the point where you can use them as training devices for children and anybody else who might need it before they can afford a full prosthetic device. So what we found is with any about 95 Shore adurometer thermoplastic polyurethane or any elastomer, we can actually vary the printing with the walls, ceilings, infill percentage, and the infill patterns of what we're printing. And we can replicate Shore durometers ranging everything from 10A all the way to 95A. And what this allows you to do is we can actually take a model of a human hand and we can actually, on a desktop printer, we can print a solid structure inside and then we can print with an elastomer on the outside that replicates the tissue depth of a normal human hand. What this does is now instead of printing like robots, we're actually going on and replicating what it feels like to have a human hand on you. So there's a lot of benefits from this, especially to feel about the user and the people interacting with the device especially. So first of all, this can be easily printed from standard solutions. We're not doing anything that requires any special hardware. All you have to do is put it through our slicing software, and we can actually generate certain patches to have certain durometers when the part is printed. Also, this can easily be applied to a whole lot more than just limbs. Not only do we want limbs and things to be soft, but think about what if your armrest or what if another part you have, maybe a table or something, has parts of it that were soft, and you could tune the softness of that material and make it a little better to interact with than simply a hard part. For the user especially, this makes artificial limbs feel a lot more human. And what this does, it's really important with children because they really don't want to feel left out or different than anybody else. And what we can do, we've now hit the phase that, yes, we can make robotic arms, we can make you look cool, we can make you look like the Terminator. But now we can actually push that further and we can bring this in where we can have a low-cost solution that brings tissue back onto the hands. And when you're interacting with someone, if you shake the hand, it feels like you're shaking a normal person's hand. And also with the fingerprints, this allows little kids, whenever you're doing a project or something, not only can they design their own fingerprint and restore that piece of identity, but these, using elastomers, we can actually stamp and use this just like any other normal piece of human tissue. Also, this is a huge thing with grasping abilities. So if you think about an exoskeleton, it's like walking around all day with a pair of plastic chopsticks trying to pick everything up. So even if you can grasp something, that doesn't mean you can hang on to it. And tissues really, really help with that. If you think about everything you do in your normal life, how much more difficult would it be if you didn't have any tissues on your bones? So anything from grasping a smooth object like a door handle, it'd be very hard to turn without tissue. Even resting your hands against a table, it'd be very hard to not have your arms slipping off if you didn't have any tissue. Yeah, so that's what me and my group are doing at University of Michigan, replicating tissue durometers with standard desktop printable materials. Thank you.
Well, thanks to Aaron and thanks to all the presenters. 9 great presentations. Now you can begin voting on the app right now, right at 1:30. And the winner will be announced tomorrow morning at 8 o'clock at the beginning of the keynote presentation. So one last time, I'd like to thank our judges, Brian Levy, Boris Fritz, Brenna Snyderman, and Carl Decker. Thanks to them, and thanks to everybody for the terrific presentations. And the winner, again, will be announced tomorrow morning at 8 o'clock, and you can begin voting on the app right now. Thank you.